In the early attempts to reach the deepest parts of the ocean, engineers lowered experimental submersibles into waters that seemed to erase all familiar reference points long before the seafloor was reached, where darkness thickened into something almost absolute, and every instrument reading began to behave as if it belonged to a different world entirely. In places like the Mariana Trench, early descents were expected to confirm a kind of emptiness at the bottom, yet what came back from those rare and fragile missions began to introduce details that did not fully align with what scientists thought the deepest ocean would be like. If something was discovered at the very bottom of the ocean, why did so few of those missions ever return there again in the same way? In this investigation, you will follow how those few journeys downward revealed unexpected traces in environments assumed to be untouched, and how those findings slowly shaped the decision to limit how often humanity went back to the deepest places on Earth, the last frontier beneath us. Far from the world's coastlines, beyond the reach of sunlight and weather, lies a realm so vast that much of it remains unseen even today. It covers more than 70% of Earth's surface, shapes global climate, influences the chemistry of the atmosphere, and conceals landscapes larger than entire countries. Yet for most of human history it existed as little more than a dark boundary beneath the waves, a place known only through fragments brought back by nets, anchors, and chance encounters. While mountains could be climbed and deserts crossed, the depths remained hidden beneath a moving ceiling of water, offering almost no clues about what waited below. The deeper the ocean became, the more completely it erased evidence of its own existence, leaving generations to wonder what might be concealed in the darkness far beneath their ships. For thousands of years, humanity's relationship with the sea remained largely confined to its surface. Ancient civilizations crossed oceans, mapped coastlines, and built entire economies around maritime trade, but the deep ocean itself remained inaccessible. Sailors could measure depth using weighted ropes, yet those measurements revealed little beyond numbers. Occasionally a line descended farther than expected and returned with traces of mud or fragments of unfamiliar life, hinting that an unseen world existed below. These rare clues fueled speculation. Some imagined underwater kingdoms. Others feared monstrous creatures lurking beyond the reach of light. In reality, nobody knew. The ocean floor was as mysterious to 19th century explorers as the far side of the moon would be to later generations. Scientific curiosity gradually replaced mythology as technology improved. During the 19th century, expeditions began collecting systematic information about the oceans. One of the most significant voyages departed in 1872 when the British research vessel HMS Challenger embarked on a nearly 4-year scientific expedition. Travelling tens of thousands of miles across the world's oceans, the crew measured depths, collected samples, and documented marine life on a scale never attempted before. The expedition revealed that the deep sea was not an empty abyss as many had assumed. Strange organisms lived in places once believed incapable of supporting life. Vast underwater landscapes existed beyond sight of any coastline. The findings transformed oceanography into a serious scientific discipline, but they also exposed a humbling reality. Almost everything beneath the surface remained unknown. Despite these discoveries, observing the deep ocean directly remained impossible. Scientists could recover samples, but they could not witness the environment where those samples originated. The challenge was not distance, but pressure. Water is deceptively heavy, and pressure increases rapidly with depth. At just 1,000 meters below the surface, the force exerted by the surrounding water becomes immense. Far deeper, the pressure reaches levels capable of crushing conventional equipment as though it were made of paper. This invisible barrier prevented humans from entering the abyss for decades, no matter how strong their curiosity became. A breakthrough arrived through the determination of a naturalist named William Beebe and an engineer named Otis Barton. Together, they pursued an idea that sounded almost impossible for its time. Instead of relying solely on dredges and nets, they would descend into the ocean themselves. Their solution was the bathysphere, a steel sphere designed to withstand crushing pressure while suspended from a cable attached to a ship above. The vessel was primitive compared to modern standards. Its occupants depended entirely on the cable connecting them to the surface. If that connection failed, survival would be unlikely. In 1930, experimental descents began near Bermuda. Beebe and Barton entered the cramped steel chamber, and watched sunlight gradually disappear as they descended into increasingly unfamiliar waters. Through small quartz windows, they observed creatures that few people had ever seen alive. Bioluminescent organisms flashed in the darkness. Fish appeared with strange shapes adapted to conditions unlike anything at the surface. Each descent pushed farther than before, culminating in a record-setting dive in 1934 to a depth of approximately 923 meters. Though modest compared to later achievements, the journey represented a revolutionary moment. For the first time, human beings had directly observed a substantial portion of the deep ocean environment. The bathysphere revealed something unexpected. Rather than becoming empty with increasing depth, the ocean remained populated by life forms adapted to extreme conditions. Darkness did not signify lifelessness. Instead, it concealed ecosystems that had evolved beyond human observation. These discoveries challenged long-standing assumptions and intensified scientific interest in exploring deeper waters. If such remarkable organisms existed within reach of the bathysphere, what might await farther below? The decades that followed brought rapid technological development. Engineers sought ways to free deep-diving vessels from their dependence on surface cables. This effort led to the creation of the bathyscarf, a vehicle capable of descending independently through the water column. Unlike the bathysphere, which relied on a ship for support, the bathyscarf carried buoyancy systems that allowed it to operate more autonomously. Among these vessels, one would become particularly famous. Built and refined by Swiss physicist Auguste Piccard and later operated with the involvement of his son Jacques Piccard, it represented a major step toward reaching the deepest places on Earth. The pursuit of greater depth reflected more than scientific ambition. During the 20th century, exploration increasingly became a measure of technological capability. Nations invested enormous resources into aviation, polar expeditions, and eventually spaceflight. Yet while rockets captured public attention, another frontier remained largely invisible. The ocean floor covered an area larger than all the continents combined, but very little of it had been mapped in detail. Scientists knew more about the surface of some celestial bodies than they did about large portions of their own planet. As attention turned towards space during the 1950s and 1960s, oceanographers often drew comparisons between the two frontiers. The comparison was not merely rhetorical. Both environments were hostile to human survival. Both required specialized vehicles. Both concealed unknown landscapes beyond ordinary observation. Yet the deep sea possessed a unique challenge. Space is a vacuum, but pressure decreases as altitude increases. In the ocean, pressure relentlessly intensifies. Every meter downward increases the forces acting upon explorers and equipment. This made extreme depths extraordinarily difficult to reach, and even more difficult to study. The challenges extended beyond engineering. Communication beneath the ocean remained limited. Navigation became increasingly complicated as depth increased. Darkness prevented visual observation over long distances. Even locating a specific site on the seafloor could require enormous effort. Researchers often spent years planning missions that would provide only brief opportunities for direct observation. The ocean resisted exploration at nearly every stage. Nevertheless, progress continued. Advances in sonar technology began revealing hidden features of the seafloor. Mountain ranges thousands of kilometers long emerged from the data. Vast trenches appeared in regions previously considered featureless. Underwater volcanoes, ridges, and canyons reshaped scientific understanding of Earth's geology. The discovery of the Mid-Atlantic Ridge and the mapping of other underwater structures contributed to the development of plate tectonic theory, one of the most important scientific breakthroughs of the 20th century. The deep ocean was no longer viewed simply as a repository of strange creatures. It became recognized as a dynamic environment that played a fundamental role in shaping the planet itself. Even with these advances, the proportion of the ocean directly observed by humans remained astonishingly small. Most information still came from instruments rather than eyewitness exploration. Researchers frequently compared the situation to attempting to understand an entire continent by examining only a handful of scattered locations. Every expedition seemed to reveal something unexpected. New species appeared regularly. Geological formations challenged assumptions. Previously unknown ecosystems emerged where scientists had not expected them. By the late 20th century, remotely operated vehicles and advanced submersibles expanded humanity's reach. These machines could descend far beyond the limits of conventional diving and remain underwater for extended periods. Cameras transmitted images from places no human could safely visit. The footage often appeared almost extraterrestrial. Giant tube worms clustered around hydrothermal vents. Delicate organisms drifted through perpetual darkness. Predators illuminated the water with flashes of bioluminescent light. The deeper researchers explored, the more unfamiliar the environment became. This growing awareness led many scientists to describe the deep ocean as Earth's true final frontier. The phrase reflected a simple reality. Vast portions of the moon had been photographed in detail. Satellites mapped nearly every corner of the planet's surface from orbit. Yet enormous regions of the seafloor remained poorly understood. Even in the 21st century, high-resolution mapping covered only a fraction of the ocean bottom. Entire underwater mountain ranges, trenches, and ecosystems awaited detailed study. The mystery was not merely geographic. Fundamental scientific questions remained unanswered. How many species inhabit the deep sea? What adaptations allow organisms to survive under crushing pressure? How does life persist in environments without sunlight? What geological processes continue unseen beneath the waves? Each answer seemed to generate additional questions. Exploration rarely reduced the mystery. Instead, it revealed how much more remained hidden. Public fascination occasionally surged whenever a dramatic expedition captured headlines, but the deep ocean rarely maintained the same visibility as space exploration. There were no distant planets visible in the night sky to inspire imagination. The abyss existed directly beneath Earth's oceans, concealed beneath an ordinary surface that gave little indication of what lay below. Yet the scale of the unknown remained staggering. Researchers estimated that countless marine species had yet to be documented. Entire ecosystems likely existed beyond the reach of existing surveys. The paradox became increasingly apparent. Humanity had built machines capable of travelling beyond Earth, landing on other worlds, and observing distant galaxies, yet vast areas of its own planet remained largely unexplored. The deep sea was not a relic of the past waiting to be rediscovered. It was an active frontier, continuously shaping the Earth's climate, geology, and biological diversity while remaining hidden from everyday view. For all the technological achievements that followed, one destination continued to exert a particular pull on explorers and scientists alike. Hidden within the western Pacific Ocean was a place deeper than any other known location on Earth, a trench descending so far beneath the waves that it seemed almost disconnected from the world above, and reaching it would require a journey unlike any attempted before. This next objective lay at the bottom of a depression so extreme that even the pioneers of deep-sea exploration could only guess what might be waiting there. Into the abyss, the first descent to Challenger Deep. What lay at the bottom of that immense depression remained one of the most persistent unanswered questions in ocean exploration. Scientists had measured extraordinary depths within the Mariana Trench, a crescent-shaped scar in the western Pacific Ocean stretching for more than 1,000 miles. Yet measurements alone could not reveal the character of the place itself. Numbers suggested that parts of the trench descended farther than Mount Everest rose above sea level, but no human being had ever looked upon its floor. The deepest known location on Earth existed largely as an abstraction, represented by charts, calculations, and echo-sounding data. Somewhere beneath miles of water was a landscape that had never been directly observed, and despite decades of progress in ocean exploration, nobody could say with certainty what would be waiting there. Across thousands of square miles of the western Pacific, no location inspired more fascination among oceanographers than the deepest known point within the Mariana Trench. The feature would later become widely known as Challenger Deep, named after HMS Challenger, whose pioneering scientific expedition in the 19th century had helped reveal the existence of profound ocean depths. Further surveys refined those measurements, confirming that a region of exceptional depth lay hidden beneath the Pacific. Yet the trench remained frustratingly inaccessible. Unlike a mountain summit, which could at least be photographed from afar, the bottom of Challenger Deep was concealed beneath nearly 7 miles of water. Every attempt to understand it depended upon instruments lowered from ships on the surface, and those instruments could reveal only fragments of the story. Inside a vessel built to withstand forces beyond ordinary comprehension, two men prepared to enter a realm that existed almost entirely beyond human experience. One was Jacques Piccard, the Swiss engineer and explorer whose family had become closely associated with pioneering work in extreme environments. The other was Lieutenant Don Walsh of the United States Navy. Together they would descend aboard the Bathyscaphe Trieste, a remarkable craft unlike conventional submarines. Suspended beneath a large gasoline-filled float was a small pressure sphere designed to protect its occupants from the immense forces of the deep ocean. Compared to the vastness of the trench they intended to enter, the compartment was astonishingly small. For hours, the two men would occupy a space barely large enough for them to move comfortably, carrying with them humanity's hopes of reaching a place no person had ever visited. Shortly after the descent began, the familiar world of waves, weather and daylight started to disappear above them. On January 23, 1960, the Trieste began its historic dive near Guam. At first, the descent passed through waters that still contained traces of sunlight. Conditions outside the vessel gradually darkened as depth increased. The surface, with its shifting skies and open horizon, receded into a distant memory. Unlike explorers crossing deserts or climbing mountains, Piccard and Walsh could not look ahead and see their destination. Everything beyond the vessel's small windows was increasingly obscured by darkness. The deeper they travelled, the more complete their separation from the world above became. Hour after hour, the Trieste continued downward through water that grew darker, colder, and increasingly alien. The descent was deliberately slow, requiring patience as much as courage. There were no dramatic landmarks passing by outside the viewport, no visible signs marking progress toward the bottom. Instead, depth was measured through instruments and calculations. The ocean surrounding them became a vast, nearly featureless void. For much of the journey, there was little to see beyond occasional particles drifting through the water. Yet that emptiness carried its own significance. Every passing minute carried the explorers farther from any location previously visited by human beings. From within the cramped pressure sphere, even the smallest sound carried unusual significance. The deep ocean exerted extraordinary pressure on every external component of the vessel, and although the Trieste had been carefully designed for the mission, uncertainty remained an unavoidable companion. During the descent, Piccard and Walsh heard noises that drew their attention. One particularly sharp sound raised concerns about possible damage to part of the craft. Later accounts would describe how an outer acrylic window had developed a crack, creating understandable anxiety. At such depths, there could be little room for error. The explorers had committed themselves to a journey from which immediate rescue would be impossible. Every system aboard the vessel needed to continue functioning as intended. Few journeys in the history of exploration had ventured so completely beyond the boundaries of direct human knowledge. Earlier generations had crossed oceans, mapped continents, and reached remote polar regions, but those explorers entered environments that could still be observed and described from a distance. Challenger Deep was different. No human experience existed to guide expectations. Scientists could estimate temperature, pressure, and depth, yet the appearance of the seafloor remained unknown. The possibility of unexpected discoveries lingered throughout the descent. In many ways, Piccard and Walsh were travelling toward one of the last places on Earth that still retained the quality of a blank space on the map. As the depth increased, the significance of the mission extended beyond the two men inside the vessel. Their descent represented the culmination of decades of technological development that had begun with the earliest bathyspheres and evolved through successive generations of engineering innovation. Every successful test, every improvement in materials, and every lesson learned from previous dives had contributed to this moment. The Trieste itself had undergone modifications after its acquisition by the United States Navy, specifically to prepare it for extreme depth operations. Reaching Challenger Deep would not simply establish a new record. It would demonstrate whether human beings could physically enter the deepest known part of the ocean and return safely. Nearly 5 hours after leaving the surface, a faint cloud of disturbed sediment signaled that the descent had finally come to an end. The Trieste had reached the bottom of Challenger Deep. The achievement was unprecedented. After generations of speculation and decades of technological advancement, human beings had arrived at the deepest known location on Earth. Yet the moment itself was surprisingly subdued. There was no dramatic vista waiting beyond the window, no towering geological formation announcing their arrival. Instead, The disturbance created by the vessel's descent reduced visibility, stirring fine sediment from the seafloor. The explorers had reached their destination, but the trench was not prepared to reveal its secrets all at once. Beyond the small viewing window, the deepest known seafloor on Earth appeared far different from what many had imagined. Popular imagination often portrayed extreme environments as dramatic landscapes filled with extraordinary sights, yet Challenger Deep presented a quieter scene. The visible terrain appeared relatively flat and covered with soft sediment. The impression was one of stillness rather than spectacle. For a brief period, Pickard and Walsh observed the environment around them, documenting what they could from their limited vantage point. The significance of the moment lay not in dramatic visuals, but in the simple fact that human eyes were witnessing a place that had remained hidden throughout all of recorded history. Among the observations reported during the dive was the sighting of what appeared to be a flatfish-like creature near the seafloor. At the time, the observation attracted considerable attention because it seemed to suggest the presence of vertebrate life at extraordinary depths. Later scientific analysis raised questions about the identification. Some researchers argued that the animal may have been a different type of organism altogether, perhaps a sea cucumber or another invertebrate viewed under unusual conditions. The debate remains a fascinating reminder of how difficult observation can be in extreme environments. Even after reaching the deepest place on Earth, certainty remained elusive. The trench had yielded observations, but not necessarily definitive answers. Rather than resolving the mystery of the trench, the brief observations made at the bottom introduced new uncertainties. Scientists now possessed direct evidence that the seafloor could be reached, yet the limited duration of the visit left countless questions unanswered. The explorers spent only a short time at the bottom before beginning their ascent. There were no extensive surveys, no detailed mapping operations, and no opportunity to travel across large sections of the trench. The mission had been designed primarily to achieve the descent itself. As a result, humanity's first visit to Challenger Deep resembled a brief glimpse through a partially opened door rather than a comprehensive exploration. The achievement immediately secured a place in the history of exploration. Newspapers around the world reported the successful dive, and the names of Jacques Piccard and Don Walsh became associated with one of the greatest feats of deep-sea exploration ever accomplished. Yet the mission's deeper significance emerged gradually. It demonstrated that the greatest depths of the ocean were not permanently beyond human reach. The trench could be visited. The challenge, however, was turning a single extraordinary journey into sustained exploration. Reaching the bottom once was a triumph. Understanding it would require far more effort. With their objectives completed and their time at depth limited, the long return toward daylight soon began. The ascent required several hours, providing ample opportunity to reflect upon what had just occurred. Somewhere below them remained the deepest known point on Earth, a place that had finally been touched, yet remained largely unexplored. The voyage had transformed Challenger Deep from an abstract measurement into a real location visited by human beings, but its mysteries remained remarkably intact. If anything, the mission underscored how little could be learned from a single encounter with such an immense and inaccessible environment. For all the attention the expedition would later receive, its most important legacy was not the record it set, but the questions it left behind. What other forms of life existed in the deepest trenches? How representative were the observations made during those few minutes on the seafloor? What geological processes shaped such extreme environments over millions of years? The answers would not arrive quickly. In fact, decades would pass before humans again returned to Challenger Deep. The historic descent had succeeded beyond expectations, yet it also revealed the limits of what even the most ambitious expedition could accomplish during a single visit to the abyss. Hidden beneath every observation was a simple reality. Reaching the deepest place on Earth had required confronting forces so extreme that they would shape every future attempt to explore the abyss. The ocean that crushes everything. The achievement was undeniable, but the long silence that followed was far more revealing. Jacques Piccard and Don Walsh had proven in 1960 that human beings could reach the deepest known place on Earth, yet years passed before anyone attempted to repeat the feat. The question lingered in the background of ocean exploration. If the bottom of Challenger Deep had already been reached, why did so few people return? The answer was not hidden within a lack of scientific interest. On the contrary, researchers were eager to learn more about the abyss. The problem was that every descent into the deep ocean required confronting an environment that continuously resisted human presence. Reaching the seafloor was never simply a matter of travelling downward. It meant surviving conditions unlike those found anywhere else on the planet. While rockets carried astronauts beyond the atmosphere, the deepest reaches of the ocean remained largely untouched. This contrast often surprises people because space exploration is commonly viewed as humanity's greatest technological challenge. Yet many oceanographers and engineers have pointed out that certain aspects of deep-sea exploration are uniquely difficult. A spacecraft operates in a vacuum, while a submersible must withstand an environment that becomes increasingly hostile with every meter of depth. The ocean surrounds an explorer on all sides, applying relentless force without pause. Unlike a mountaintop or an orbital trajectory, there is no safe place to stop and regroup in the abyss. Every moment spent at depth depends upon the continued integrity of machines specifically designed to survive one of the most extreme environments on Earth. Hidden within every meter of descending water was a force that grew steadily more destructive. Water appears familiar and harmless at the surface, yet its weight accumulates with extraordinary speed. Pressure increases by roughly 1 atmosphere for every 10 meters of depth. Divers operating in relatively shallow waters already experience significant changes compared to conditions at the surface. Thousands of meters below, the numbers become difficult to imagine. At the deepest parts of the Mariana Trench, pressure exceeds 1,000 times the atmospheric pressure experienced at sea level. This force is invisible, silent, and constant. Unlike storms or waves, it offers no warning signs. It simply exists, waiting to exploit the smallest weakness in any object that enters its domain. By the time a vehicle approaches the deepest trenches, the surrounding conditions bear little resemblance to those at the surface. Engineers often rely on comparisons to convey the magnitude of deep ocean pressure. One frequently cited example suggests that pressure at Challenger Deep exceeds the weight of dozens of large passenger jets pressing against an area roughly the size of a human body. Although such comparisons simplify a complex reality, they illustrate an important point. Human beings are not naturally equipped to survive these conditions. Neither are most machines. Materials that perform reliably on land can fail catastrophically under extreme pressure. Components that appear durable in ordinary circumstances may become vulnerable once they are subjected to forces measured in thousands of pounds per square inch. Designing a craft capable of surviving such depths quickly became one of engineering's most demanding challenges. Strength alone was never enough. An object can be incredibly strong and still fail if its design concentrates stress in the wrong place. Engineers learned that deep-diving vessels required careful attention to shape, materials, and structural integrity. Spheres became particularly important because they distribute pressure more evenly than many other forms. Even then, construction standards had to be exceptionally precise. Tiny imperfections that might be insignificant elsewhere could become serious liabilities in the deep ocean. Every bolt, seal, weld, and viewing port demanded careful scrutiny because the surrounding environment offered little forgiveness for mistakes. Lessons about the ocean's power were often learned through equipment failures. Throughout the history of ocean exploration, researchers have watched expensive instruments vanish into the abyss after cables snapped or components malfunctioned. Cameras stopped functioning, sensors failed under pressure, sampling devices became trapped or damaged. The deep ocean has consumed countless pieces of scientific equipment, each loss serving as a reminder of how difficult it is to maintain reliable operations far below the surface. Even successful missions frequently encounter unexpected technical problems. The deeper an expedition travels, the more opportunities exist for something to go wrong. Sunlight surrenders surprisingly early in the ocean's vast vertical expanse. Many people imagine the sea as a bright environment because most encounters occur near beaches, reefs, or the surface. In reality, sunlight penetrates only a limited distance into the water. As depth increases, different wavelengths disappear until darkness eventually becomes complete. Beneath roughly 1,000 meters, the ocean exists in a state of perpetual night. No sunrise ever reaches these depths. No seasonal change alters the darkness. For explorers descending into the abyss, artificial lights become the only means of seeing the surrounding environment. Beyond the reach of those lights, an immense darkness stretches in every direction. Permanent darkness creates challenges that extend far beyond simple visibility. human beings rely heavily on sight to understand their surroundings. In the deep ocean, visual references are often absent. A submersible may travel through vast areas without encountering obvious landmarks. Distances become difficult to judge. Orientation can feel uncertain. Researchers frequently describe the experience as moving through an environment that resembles outer space more than anything familiar on Earth. Yet even that comparison has limits. Astronauts can see stars, planets, and distant horizons. Deep-sea explorers often see only darkness interrupted by the narrow beam of their own lights. Separated from the surface by miles of water, explorers encounter another obstacle that cannot be measured in pressure alone. Communication becomes increasingly complicated as depth increases. Radio waves, which make modern communication systems possible, do not travel effectively through seawater. As a result, conventional methods of maintaining contact become impractical beneath the ocean. Specialized acoustic communication systems can transmit information underwater, but these systems operate under significant limitations. Messages may be delayed, simplified, or constrained by environmental conditions. The deeper an expedition travels, the more isolated it becomes from the world above. This isolation creates practical challenges during emergencies. When problems occur aboard a spacecraft, communication with mission control is often immediate. Deep-sea operations do not always enjoy the same advantage. A submersible operating thousands of meters below the surface cannot rely on rapid intervention from support crews. Rescue options become extremely limited. Any malfunction must often be addressed by the crew or the vehicle itself. This reality places enormous importance on preparation and redundancy. Deep ocean explorers frequently carry backup systems because assistance may be hours away, if it is possible at all. Mechanical reliability becomes a fragile concept in an environment where failure is often swift and unforgiving. Electronic systems that perform flawlessly on land may behave differently under extreme pressure and low temperatures. Batteries must continue operating despite difficult conditions. Seals must prevent water intrusion. Cameras must function despite darkness and pressure. Navigation systems must provide accurate information in an environment where traditional methods of positioning become difficult. Every successful deep-sea mission depends upon numerous technologies working together simultaneously. The failure of a single critical component can jeopardize an entire expedition. Compounding these difficulties is the immense scale of the territory researchers hope to understand. The ocean covers more than 70% of Earth's surface, and much of that area lies far from coastlines and ports. Reaching a study site can require days or even weeks of travel aboard research vessels before any scientific work begins. Once on location, weather conditions may interfere with operations despite meticulous planning. Equipment deployment can consume significant amounts of time. Recovering instruments from great depths often requires patience and precision. The logistical complexity of ocean exploration extends far beyond the descent itself. Few comparisons challenge common assumptions more than the one often made between the abyss and outer space. The comparison is not intended to diminish the accomplishments of astronauts. Spaceflight remains one of humanity's greatest achievements, yet the analogy highlights the unique nature of the deep ocean. Both environments require life support systems, specialized vehicles, and advanced technology. Both are dangerous. Both remain only partially explored. The difference lies in the physical conditions. Spacecraft primarily keep pressure inside. Deep-sea vehicles primarily keep pressure outside. Every descent into the abyss becomes a struggle against forces actively attempting to crush the vessel carrying its occupants. Behind every successful deep-sea mission lies an extraordinary amount of preparation rarely visible to the public. Engineers test systems repeatedly before deployment. Research teams spend months planning objectives. Ships must be equipped to launch and recover specialized equipment safely. Weather forecasts are studied carefully. Contingency plans are developed for potential failures. By the time a submersible finally enters the water, years of work may already have been invested in the mission. The dramatic images captured during exploration often represent only a small fraction of the effort required to obtain them. Viewed together, these obstacles reveal why the deep ocean continues to resist even the most advanced technology. Pressure threatens structural integrity. Darkness limits observation. Isolation complicates communication. Equipment remains vulnerable to failure. The sheer size of the ocean slows progress. None of these challenges exist independently. Instead, they reinforce one another, creating an environment where exploration remains difficult despite decades of technological advancement. Every successful expedition represents a negotiation with conditions that cannot be controlled, only endured. Against all expectations, some of the most important discoveries emerged not in spite of these harsh conditions, but because of them. The same forces that made exploration so difficult also concealed environments that few scientists believed could exist. Researchers descending into remote regions of the seafloor expected to find landscapes shaped by darkness and scarcity. Instead, they would encounter something that challenged fundamental assumptions about life on Earth. Hidden in places where sunlight never reached and pressure remained immense, evidence awaited that would force scientists to reconsider how living systems could survive and thrive. What researchers eventually found rising from the darkness would overturn assumptions about where life could exist and how the planet itself functions. Cities of fire on the ocean floor. Emerging from the darkness of the Galapagos Rift was a discovery that did not align with any existing expectation of the deep ocean. The seafloor in this region of the Eastern Pacific had long been understood through the language of geology, a place where tectonic plates slowly separated and new crust formed in near silence. Yet nothing in that framework suggested the presence of dramatic activity capable of reshaping assumptions about life itself. When the first signals returned from the deep, they did not announce a single breakthrough or anomaly, but instead hinted at a pattern that seemed to contradict the prevailing image of the abyss as a cold, static, and largely unchanging environment. The deeper the observations continued, the more difficult it became to interpret the seafloor through familiar categories, as though the ocean was revealing something that had been operating beneath scientific awareness for far longer than anyone had realized. For much of modern scientific history, a seemingly simple idea guided thinking about life on Earth. Sunlight was considered the foundation of nearly all biological systems, directly or indirectly sustaining ecosystems from forests to coral reefs, and even the smallest microbial communities near the surface. Energy flowed downward through food chains that ultimately depended on photosynthesis, and anything removed from sunlight was assumed to exist at the margins of biological possibility. The deep ocean, in this view, was a vast extension of scarcity, where organic materials slowly drifted downward from above, providing minimal sustenance for sparse and specialized life forms. This framework shaped expectations so completely that few researchers considered the possibility that entire ecosystems might operate independently of sunlight, sustained instead by processes occurring far beneath the seafloor. During 1977, a deep-sea expedition operating near the Galapagos Rift deployed research instruments into a region shaped by active seafloor spreading. The mission was not initially designed to search for biological surprises, but to study geological processes associated with plate tectonics, a field that was rapidly transforming understanding of Earth's structure during the 20th century. The area itself was already known to be geologically dynamic, with magma rising from beneath the crust to form new oceanic floor as tectonic plates gradually moved apart. The expectation was that measurements would refine existing models of volcanic and geothermal activity, offering clearer insight into how the planet continuously reshapes its surface over time. Instead, the data began to suggest something far less predictable was occurring beneath the seafloor. Measurements transmitted from the ocean floor began returning values that did not align with expectations for a supposedly stable deep-sea environment. Temperature readings, chemical signatures, and other indicators suggested localized areas of intense heat and unusual composition, far removed from the uniform cold typically associated with deep water. These anomalies were not isolated incidents, but appeared in patterns that hinted at structured geological activity rather than random variation. The challenge for researchers was not only the unexpected nature of the data, but the difficulty of interpreting it within existing models. The deep ocean was assumed to be relatively uniform in physical conditions, yet the signals emerging from the Galapagos Rift suggested sharply defined zones of energy exchange, occurring in ways that had not been previously documented. As the submersible Alvin moved slowly across the rift zone, subtle changes in the terrain suggested something unusual beneath the sediment. Alvin, operated by the Woods Hole Oceanographic Institution, had already become one of the most important tools in deep-sea exploration, capable of carrying researchers directly to the ocean floor for extended observation. During dives in the rift region, the vehicle encountered variations in temperature and visual structure that did not match surrounding areas. The seafloor was no longer simply a uniform expanse of sediment, but appeared interrupted by irregular formations that hinted at active processes below. These observations accumulated gradually without immediate explanation, creating a sense that the environment itself was behaving in ways that defied established expectations. Jets of mineral-rich fluid suddenly became visible, rising from fractures in the crust in a way that defied conventional descriptions of the deep ocean. These emissions were not gentle seepages but dynamic flows, carrying heated water laden with dissolved minerals from beneath the Earth's crust into the surrounding ocean. The contrast between the superheated fluid and the surrounding near-freezing seawater created visible interactions that resembled smoke, rising from chimneys on the seafloor, forming structures that later became widely known as hydrothermal vents. Some of these formations expelled dark, particle-rich plumes that gave rise to the informal term black smokers, a description that captured their striking appearance even as their underlying mechanisms were still being understood. Surrounding these vent structures was an unexpected density of biological activity that immediately challenged assumptions about deep-sea scarcity. Instead of the sparse distribution of organisms typically associated with extreme depths, researchers observed concentrated clusters of life arranged around the vent openings. This pattern suggested not only that life could exist in such environments, but that it could thrive in localized abundance where conditions differed dramatically from the surrounding seafloor. The concentration of organisms around these vents created a stark visual contrast between seemingly barren sediment and densely populated biological communities existing only a short distance away. Among the first organisms observed were elongated tube worms clustered in vast numbers around the vent openings. These creatures, later identified as Riftia pachyptila, displayed an unusual adaptation that allowed them to inhabit environments saturated with chemicals toxic to many forms of life. Instead of relying on conventional feeding methods, they existed in close association with internal bacterial symbionts capable of processing chemical compounds emitted from the vents. This relationship represented a form of biological organization that was unlike most surface ecosystems, where energy is typically derived from sunlight. The presence of these organisms in such extreme conditions raised immediate questions about how energy flow could be sustained in environments completely detached from photosynthetic input. At the center of the scientific shock was a chemical process that bypassed sunlight entirely as a source of energy. This process, later identified as chemosynthesis, involved microorganisms deriving energy from chemical reactions involving substances such as hydrogen sulfide released from the vents. In this system, chemical energy replaced solar energy as the foundation of the food chain, allowing entire ecosystems to develop in conditions previously assumed to be biologically inhospitable. The implications of this discovery extended far beyond marine biology, suggesting that life on Earth might not be universally dependent on sunlight in the way previously believed. Instead, life could emerge and persist wherever chemical energy gradients provided sufficient conditions for metabolic processes. With every new observation, the deep ocean shifted from a presumed biological void into something far more complex and self-sustaining. The idea that vast portions of the seafloor were nearly lifeless was no longer tenable in light of the dense communities surrounding hydrothermal vents. Instead of being marginal exceptions, these ecosystems suggested the possibility that the deep ocean contained networks of life adapted to conditions radically different from those at the surface. Each new vent system studied revealed variations in species composition, chemical conditions, and geological activity, reinforcing the sense that these environments were not isolated curiosities, but part of a broader and previously unrecognized pattern. Following the initial discovery, additional expeditions soon confirmed that similar vent systems existed in multiple regions across the global seafloor. Hydrothermal vents were not confined to a single geological setting, but appeared along mid-ocean ridges and tectonically active zones around the world. This realization transformed the initial discovery from a local anomaly into a global phenomenon. The deep ocean was no longer viewed as a largely uniform environment, interrupted only occasionally by geological activity. Instead, it contained a dynamic network of chemically driven ecosystems distributed across vast distances, each shaped by the interaction of geology, chemistry, and biology in ways that were only beginning to be understood. Once the broader implications became clear, biological oceanography began reinterpreting what it meant for life to exist in extreme environments. The discovery of hydrothermal vent ecosystems challenged the assumption that sunlight was a necessary condition for complex biological communities. It also raised new questions about the origins of life itself, as some scientists began to consider whether similar chemical environments might have played a role in the earliest stages of biological development on Earth. The deep ocean, once viewed primarily as a remote and largely inactive region, became a focal point for investigating fundamental questions about biology, chemistry, and planetary evolution. Yet even as vent fields were documented in greater detail, the full extent of deep-sea ecosystems remained largely beyond direct observation. The ocean's vastness ensured that only a small fraction of hydrothermal systems could be studied in person, leaving many regions unexplored and many questions unanswered. Each new discovery suggested that there were still countless environments hidden beneath the ocean surface, waiting to be encountered. The more researchers learned, the more evident it became that hydrothermal vents were not isolated phenomena, but part of a larger and still incomplete picture of deep ocean life. Deep within these newly revealed environments, scientists encountered entire ecosystems sustained by chemical energy alone, forcing a complete reconsideration of where living systems can emerge. Creatures that should not exist. Residual uncertainties from vent ecosystems left scientists confronting a deeper and far less predictable question about life in the abyss. The discovery of hydrothermal vents had already overturned long-standing assumptions about where ecosystems could exist, yet it also exposed how limited human observation remained in the deepest parts of the ocean. Each new expedition suggested that entire biological systems were operating in conditions once considered incompatible with complex life, and yet those systems represented only a fraction of what might still be hidden beneath thousands of meters of water. The deeper researchers looked, the more evident it became that the story of deep ocean biology had only just begun, and that many of its most significant chapters remained unwritten. Biology, as it was traditionally defined, depended on a limited framework of environmental conditions and energy transfer systems. Life was understood through observable dependencies, most notably the reliance on sunlight as the foundation of nearly all ecosystems on Earth. Photosynthesis shaped expectations about energy flow, while food chains were assumed to extend outward from visible sources of primary production. Even in environments where sunlight was absent, such as caves or the deepest ocean regions, biological communities were still interpreted through indirect dependence on surface energy. This framework created a scientific baseline that appeared stable for decades, yet deep-sea exploration gradually introduced evidence that life could organize itself in ways that did not conform to these assumptions. Decades before submersibles reached extreme ocean depths, early deep-sea dredging operations were already recovering unfamiliar organisms from great pressure zones. 19th century expeditions, including those associated with the HMS Challenger voyage, collected samples from depths previously thought to be largely uninhabitable. The organisms retrieved from these early efforts often appeared radically different from known coastal species, possessing adaptations that reflected environments shaped by darkness, pressure, and isolation. Although these findings were initially limited by the technology of the time, they hinted at a broader biological diversity in the deep ocean than had been previously imagined, setting the stage for later discoveries that would challenge even more fundamental assumptions. Fragmentary accounts from historical ocean voyages occasionally referenced enormous cephalopods, whose full bodies were never directly observed. These reports, often derived from partial remains or fleeting surface encounters, contributed to long-standing scientific uncertainty regarding the existence and scale of deep-sea giants. Over time, improved documentation and rare but direct observations confirmed the presence of large squid species inhabiting deep waters, including the giant squid, Architeuthis dux. Despite confirmation of their existence, these organisms remained elusive, rarely seen alive in their natural environment, reinforcing the idea that some of the ocean's most remarkable inhabitants might spend their entire lives beyond direct human observation. In environments completely removed from sunlight, evolutionary processes produce biological forms that appear increasingly detached from surface-based expectations. Without the visual cues and energy sources that define shallow water ecosystems, deep-sea organisms develop survival strategies shaped by entirely different pressures. The absence of light eliminates the possibility of vision-based interaction for many species, while extreme pressure and low temperatures impose additional constraints on biological structure. Over time, these conditions have produced organisms that prioritize efficiency, sensitivity to subtle environmental changes, and specialized feeding strategies adapted to scarcity and unpredictability. The absence of pigmentation in many deep ocean organisms represents one of the most consistent adaptations across multiple unrelated species. In environments where sunlight never penetrates, coloration loses much of its evolutionary importance, leading to species that appear translucent, pale, or entirely colorless. This lack of pigmentation is not a singular adaptation, but rather a recurring outcome observed across different taxonomic groups inhabiting similar depths. The visual effect, when observed through submersible cameras or sampling equipment, creates an impression of biological minimalism, as though the ocean itself has stripped away unnecessary features in favor of functional survival. Sudden emissions of light within the ocean interior indicate biological systems capable of generating illumination without any external energy source. This phenomenon, known as bioluminescence, appears across a wide range of deep-sea organisms, from microscopic plankton to larger predatory species. The ability to produce light serves multiple functions, including communication, camouflage, and predation. In some cases, organisms use light to attract prey, while in others it is used as a defense mechanism, creating confusion or deterring predators. The prevalence of bioluminescence throughout the deep ocean suggests that darkness itself has become a driving force in shaping evolutionary pathways. Predatory behavior observed in abyssal environments often relies on strategies that would be ineffective in shallower ecosystems. Instead of chasing prey across open distances, many deep-sea predators depend on ambush techniques, sensory detection of minimal movement, or the use of bioluminescent lures. Some species have evolved extraordinarily large mouths and expandable stomachs, allowing them to consume prey that would otherwise be impossible to capture or digest under normal biological constraints. These adaptations reflect an environment where encounters with food may be infrequent, requiring organisms to maximize every opportunity for survival. Structural adaptations in organisms subjected to extreme pressure reveal biological limits that differ significantly from those seen near the surface. At depths reaching several thousand meters, the physical forces acting on living tissue are immense, yet deep-sea organisms have evolved cellular and biochemical mechanisms that allow them to function under these conditions. Proteins and membranes are structured in ways that maintain stability under pressure, while skeletal systems are often reduced or modified to prevent collapse. These biological adjustments demonstrate that life is not only capable of surviving extreme environments, but can also integrate those conditions into its fundamental design. Across the vast mid-water regions of the ocean, organisms exist in densities and distributions that remain difficult to fully document. These zones, extending far above the seafloor, are often referred to as the ocean's twilight or midnight regions, where light gradually fades into complete darkness. Within these layers, countless species move through a three-dimensional environment that is largely inaccessible to direct observation. Many of these organisms migrate vertically over long distances, rising towards shallower waters at night and descending during the day, creating one of the largest coordinated movements of biomass on the planet. Despite its scale, this phenomenon remains only partially understood due to the difficulty of continuous observation. Even with modern imaging systems, many deep-sea species are known only from brief or partially obscured encounters. Submersibles, remotely operated vehicles, and deep-sea cameras capture isolated moments rather than continuous behavior, often under conditions of limited visibility and short observation windows. As a result, scientists frequently reconstruct biological understanding from incomplete data, relying on fragmented footage, physical samples, and indirect evidence. This limitation introduces uncertainty into classifications and interpretations, as some organisms may behave differently when observed or may exist in forms that are only partially captured by available technology. Comparative studies across multiple ocean basins have revealed recurring patterns of adaptation that suggest convergent evolutionary responses. Despite vast geographical separation, similar environmental pressures appear to produce similar biological outcomes, including transparency, reduced metabolism, and specialized feeding mechanisms. These repeated patterns indicate that deep-sea environments exert consistent selective forces on life, shaping organisms in predictable yet unfamiliar ways. The consistency of these adaptations across different regions suggests that the deep ocean functions as a unified but highly complex evolutionary landscape. As biological surveys extend into increasingly inaccessible regions, the distinction between known and unknown life forms becomes progressively harder to maintain. Each new expedition has the potential to reveal species that do not fit neatly into existing classifications, forcing continuous revision of biological frameworks. The boundary between documented life and unexplored diversity remains fluid, shaped by the limits of observation technology, as much as by the actual distribution of organisms in the ocean. In this sense, the deep sea does not simply contain unknown life, it continually redefines the concept of biological knowledge itself. Far beyond the reach of sustained observation, isolated encounters continue to reveal organisms whose structures challenge established biological classification and understanding. The graveyards hidden beneath the waves. Beneath vast stretches of open water, another kind of record has accumulated beyond ordinary view. Unlike the ecosystems that challenged biological assumptions or the geological forces that reshaped understanding of the planet, these remnants tell stories that began at the surface and ended in darkness. They're scattered across ocean basins, resting in trenches, continental shelves, and remote regions far from shipping lanes, preserved by conditions that often prevent the passage of time from erasing them completely. For decades, and sometimes centuries, many of these sites remained beyond reach, their locations uncertain and their histories incomplete. Yet each one represents a moment when a journey stopped, communication ceased, and a chapter of human experience slipped beneath the waves. Unlike cities, monuments, or written archives, the seabed preserves history in a form few people ever witness firsthand. Cold temperatures, limited oxygen, and the absence of sunlight can slow the processes that normally destroy evidence on land, creating environments where objects remain remarkably intact long after they vanish from public memory. In some locations, wooden structures survive for centuries. In others, steel hulls retain recognizable outlines decades after sinking. These conditions transform portions of the ocean floor into an enormous historical repository, where artifacts, vehicles, and personal belongings remain suspended between preservation and decay. The deeper researchers explore, the more apparent it becomes that the ocean is not only a natural environment, but also one of the largest archives of human history on Earth. Many disappearances that once seemed destined to remain unsolved ultimately left traces in the depths below. Throughout maritime history, storms, navigational errors, mechanical failures, wartime actions, and unexplained circumstances have claimed ships and aircraft without leaving immediate answers behind. Families waited for news that never arrived. Investigations ended with uncertainty. Official reports often relied on fragments of testimony rather than direct evidence. In many cases, the ocean became the final witness, holding information beyond the reach of contemporary technology. Only years later, sometimes generations later, would advances in underwater exploration allow investigators to return and search for clues hidden beneath thousands of meters of water. Advances in underwater imaging gradually transformed the search for lost wrecks from speculation into systematic investigation. Side-scan sonar, remotely operated vehicles, autonomous underwater systems, and deep-diving submersibles expanded humanity's ability to survey regions that had once been effectively inaccessible. Instead of relying solely on eyewitness accounts or historical estimates, researchers could begin examining the seabed directly. Vast areas could be mapped in detail, revealing anomalies that hinted at human-made structures resting below. Once located, these sites often provided information unavailable from historical records alone. The ocean was no longer simply concealing evidence, it was gradually allowing it to be recovered and interpreted. Few discoveries captured global attention more than the identification of RMS Titanic, resting nearly 2.5 miles beneath the North Atlantic. Since the ship's sinking in April 1912, its final resting place had remained unknown despite decades of public fascination. Numerous searches failed to locate the wreck, reinforcing the difficulty of finding a single vessel in an ocean of immense scale. In 1985, an expedition led by Robert Ballard and Jean-Louis Michel finally discovered the remains of the ship approximately 370 miles southeast of Newfoundland. The images transmitted from the seabed revealed a vessel that had become both a historical artifact and a powerful symbol of human vulnerability. Beyond confirming the ship's location, the wreck provided new insight into the final stages of the disaster, helping researchers better understand how the vessel broke apart as it descended toward the ocean floor. Decades after major conflicts ended, the ocean continued to conceal evidence of battles fought far beyond the horizon. The First and Second World Wars sent thousands of ships beneath the surface, many disappearing in remote locations where no detailed examination was possible at the time. Merchant vessels, destroyers, cruisers, aircraft carriers, and submarines became part of an underwater landscape shaped by conflict. For years, some wrecks remained unlocated despite extensive historical records documenting their loss. Others were discovered unexpectedly during unrelated surveys, reminding researchers that the seabed still contains traces of events that altered the course of nations. Each discovery offered an opportunity to connect physical evidence with historical accounts, bringing clarity to moments that had previously been understood only through reports and recollections. Confirmation of the final location of USS Indianapolis provided historians with information unavailable for generations. In July 1945, the heavy cruiser completed a secret mission delivering components associated with the atomic bomb program before being torpedoed by a Japanese submarine in the Philippine Sea. The vessel sank rapidly, and many survivors endured days in the water before rescue arrived. The tragedy became one of the most significant naval disasters in United States history. For decades, uncertainty remained regarding the ship's exact resting place. In 2017, researchers located the wreck more than 3 miles beneath the surface. The discovery not only confirmed historical details regarding the sinking, but also provided closure for many families and historians who had spent years examining the event. Submerged aircraft often survive in conditions that preserve details long erased from comparable sites on land. Military aircraft lost during wartime and civilian planes lost in accidents have been discovered in lakes, coastal waters, and deep ocean environments where corrosion progresses slowly enough to retain significant structural features. Some discoveries have resolved long-standing mysteries regarding flight paths, mechanical failures, or final moments before impact. Others have revealed little beyond confirmation of location, preserving uncertainty even after decades of searching. The ocean's ability to preserve evidence means that aircraft recovered from underwater sites sometimes offer investigators opportunities unavailable elsewhere, turning the seabed into a source of information capable of revisiting questions long considered closed. Across remote regions of the Pacific, wrecks remain scattered across the seafloor in concentrations that resemble forgotten battlefields. Areas associated with major wartime campaigns contain ships, aircraft, and military equipment resting where they fell, creating submerged landscapes shaped by conflict. Unlike monuments constructed to commemorate events, these sites are direct remnants of history itself. The vessels remain where crews last served aboard them, while surrounding debris often reflects the intensity of battles that unfolded across immense stretches of ocean. Modern surveys have revealed the scale of these underwater historical sites, demonstrating that some chapters of the 20th century remained physically present beneath the surface, preserved in environments rarely seen by human eyes. Careful examination of these sites has occasionally challenged assumptions that persisted for decades. Historical narratives are often constructed from reports, survivor testimony, official records, and available evidence, yet underwater discoveries sometimes reveal details that were previously unknown or misunderstood. Damage patterns can clarify how a vessel sank. The location of debris fields can reshape interpretations of final events. Structural evidence may confirm or challenge long-standing theories. While wrecks do not always provide definitive answers, they often contribute information unavailable from written records alone. In this way, the ocean continues to participate in historical investigation long after the events themselves have passed into memory. Respect for the dead frequently shapes decisions about how underwater discoveries are studied and documented. Many wrecks are not simply archaeological sites, but also grave sites containing the remains of those who never returned. This reality creates ethical considerations regarding exploration, recovery, and public access. Governments, researchers, and descendants frequently debate how these locations should be treated, balancing historical inquiry against the need for preservation and respect. Some sites are protected by law, while others remain largely undisturbed because of their cultural and emotional significance. The deeper researchers venture into these submerged archives, the more they encounter questions that extend beyond science and history into remembrance itself. Collectively, these wrecks form an extraordinary historical archive extending across oceans and centuries. Merchant ships carrying goods between continents, exploration vessels charting unknown regions, naval fleets engaged in conflict, and aircraft crossing remote expanses have all contributed to a vast underwater record of human activity. Unlike traditional archives, however, this one was not intentionally created. It emerged through loss, accident, conflict, and circumstance. Every wreck preserves a fragment of a larger story, waiting for technology, opportunity, and curiosity to bring it back into view. As exploration advances, the ocean continues revealing pieces of history that were once considered permanently inaccessible. Not every mystery encountered in the deep, however, leaves behind a physical object that can be located and examined. Some phenomena appear briefly, are captured only through instruments, and vanish before a source can be identified. Unlike shipwrecks or aircraft resting on the seabed, these mysteries offer no visible structure to investigate, no debris field to map, and no historical record capable of providing immediate answers. They exist as fleeting traces moving through the water itself, challenging researchers in ways entirely different from the discoveries that came before. At times, the only evidence comes in the form of distant sounds that emerge from the darkness, are recorded for a moment, and then vanish without a clear source. The sounds nobody can explain. Only a handful of mysteries are known solely through vibrations detected in the darkness. Unlike shipwrecks that leave behind steel hulls or ecosystems that can be photographed and studied directly, certain oceanic phenomena reveal themselves only through brief acoustic traces recorded by instruments far from their source. No shape appears on a screen. No object emerges from the depths. Instead, researchers are left with patterns of sound moving through thousands of miles of water, carrying evidence that something happened somewhere beyond sight. In an environment where direct observation remains extraordinarily difficult, these fleeting signals can become some of the most puzzling clues the ocean has to offer. The recordings may last only seconds, but the questions they generate can persist for decades. Decades before many deep-sea regions could be visually explored, underwater listening stations were already collecting vast amounts of information. During the Cold War, extensive hydrophone networks were developed to monitor submarine activity across the world's oceans. One such system, known as SOSUS, or the Sound Surveillance System, consisted of underwater microphones capable of detecting low-frequency sounds over remarkable distances. While its original purpose was military, the network eventually provided scientists with an unprecedented opportunity to study natural ocean acoustics. As researchers began examining the immense quantity of data collected through these systems, they discovered that the ocean was far from silent. Every day, countless sounds traveled through the water, creating an acoustic landscape as complex and dynamic as any environment on land. Far below the waves, a continuous chorus of natural activity moves through the ocean in every direction. Earthquakes generate low-frequency rumblings that can travel enormous distances. Volcanic eruptions release bursts of acoustic energy that ripple through entire ocean basins. Massive icebergs fracture and collide near polar regions, producing sounds powerful enough to be detected thousands of miles away. Marine mammals contribute their own voices to this underwater world, with whales communicating across vast stretches of ocean through calls that can penetrate great distances. Even storms influence the acoustic environment, transmitting energy into the sea from the atmosphere above. To researchers monitoring these signals, the ocean often resembles a living network of constantly overlapping sounds, each one carrying information about processes occurring beyond direct observation. From time to time, however, instruments registered signals that did not fit neatly into familiar categories. Most recordings could eventually be linked to known sources after careful analysis, but certain events resisted immediate explanation. These sounds appeared unexpectedly, exhibited unusual characteristics, and sometimes travelled across multiple monitoring stations simultaneously. Investigators would compare frequency ranges, durations, and propagation patterns, searching for similarities to previously documented phenomena. Occasionally, a likely explanation emerged quickly. In other cases, uncertainty persisted for years. It was this small collection of anomalies that captured public attention and transformed routine acoustic monitoring into one of the ocean's most intriguing scientific mysteries. During the summer of 1997, a particularly unusual recording appeared across a network of hydrophones in the Pacific Ocean, detected by sensors operated by the National Oceanic and Atmospheric Administration. The sound was powerful enough to be recorded by multiple stations separated by thousands of miles. Its frequency characteristics differed from many familiar biological and geological sounds, and its sheer scale attracted immediate interest among researchers. The signal eventually became known as the bloop, a nickname that would spread far beyond scientific circles. Although the recording itself lasted only a short time, its unusual nature ensured that it would become one of the most discussed acoustic events ever associated with the deep ocean. Media attention soon transformed the event into one of the most widely discussed acoustic mysteries ever associated with the deep sea. Reports emphasizing the extraordinary power of the signal led to speculation about potential sources. Some observers suggested undiscovered marine organisms of enormous size. Others proposed exotic geological explanations or phenomena that had not yet been documented. The fact that the source could not be immediately identified created a vacuum readily filled by imagination. Popular discussions often drifted far beyond available evidence, turning a scientific anomaly into a cultural mystery. Yet beneath the speculation remained a genuine question that researchers continued attempting to answer through careful analysis rather than conjecture. Careful examination of the available data gradually shifted the discussion toward large-scale natural processes. Over time, scientists identified similarities between the bloop and sounds generated by ice-related events in polar regions. Fracturing ice, collisions between ice masses, and other cryogenic processes can release significant acoustic energy into the ocean, producing signals capable of traveling immense distances. NOAA later suggested that the characteristics of the recording were consistent with large ice quakes occurring near Antarctica. While this interpretation provided a plausible explanation, the bloop retained much of its mystique because the original source event was never directly observed. The mystery was reduced but not entirely eliminated, illustrating how difficult it can be to reconstruct events that occur far from human presence. Several years earlier, another unexplained sound had already attracted the attention of researchers monitoring the oceans. In March 1999, hydrophones recorded a signal that became known as Julia. Like the bloop, Julia originated somewhere within the Pacific and displayed characteristics that made immediate identification difficult. Scientists considered several possibilities, including ice-related activity, yet definitive confirmation proved challenging. The signal's origin remained uncertain enough that it continued to appear in discussions of unexplained ocean sounds long after its initial detection. Unlike mysteries resolved through direct investigation, Julia demonstrated the limitations imposed by distance, timing, and the inability to revisit an acoustic event once it has passed. Persistent rather than sudden, a phenomenon later known as upsweep presented a different investigative challenge altogether. First detected in the early 1990s, upsweep consisted of recurring low-frequency sounds originating from broad regions of the Pacific Ocean. Unlike isolated recordings that appeared briefly and disappeared, this phenomenon continued over extended periods, allowing researchers to collect substantial amounts of data. The sound exhibited seasonal variation and appeared linked to areas associated with volcanic and tectonic activity beneath the ocean. Although many scientists suspect geological processes play a central role, the precise mechanisms responsible for the recordings have not been completely established. Upsweep remains notable, not because it was entirely inexplicable, but because even prolonged observation has not produced a single definitive explanation. Additional recordings with unusual characteristics continued to emerge as monitoring networks expanded their reach. Sounds given names such as train, whistle, and slow down entered scientific discussions after exhibiting acoustic features that resisted immediate classification. In some cases, later research suggested links to ice movement, underwater geological activity, or biological sources. In others, uncertainty lingered despite extensive analysis. These recordings highlighted an important reality about ocean acoustics. Identifying a sound often requires far more information than simply detecting it. Researchers must reconstruct environmental conditions, estimate locations, evaluate propagation pathways, and compare observations against incomplete libraries of known signals. Even then, conclusions may remain tentative. Unlike light, sound can travel extraordinary distances through seawater under the right conditions. Certain layers of the ocean act as acoustic channels, allowing low-frequency signals to move across entire ocean basins with relatively little loss of energy. This property makes underwater acoustics an invaluable tool for studying remote environments, but it also complicates investigations. A sound recorded in one location may have originated thousands of miles away. Multiple pathways can distort signals during transmission, altering how they appear when finally detected. Researchers must therefore separate the characteristics of the source from the effects of the journey itself, a process that often involves substantial uncertainty. Even when likely explanations are identified, absolute certainty often remains difficult to achieve. Unlike a geological formation that can be revisited or a biological specimen that can be examined repeatedly, many acoustic events occur only once. The opportunity to observe the source directly has already passed by the time analysis begins. Scientists must work backward from recordings, piecing together evidence from timing, frequency, and environmental conditions. This method frequently narrows possibilities and can produce highly probable conclusions, yet definitive proof is not always available. Such limitations are not failures of science, but reflections of the immense scale and complexity of the ocean itself. Modern acoustic surveillance continues to reveal just how much activity occurs beyond the limits of direct observation. Every year, monitoring systems collect enormous quantities of data from oceans that remain only partially explored. Most recordings eventually find explanations rooted in geology, biology, weather, or ice dynamics. Yet the process of investigation often reveals how much remains unknown. The ocean continues generating sounds that challenge assumptions, test analytical methods, and remind researchers that even familiar environments can produce unexpected observations. Listening stations scattered across the globe function as distant observers, capturing evidence of events that may never be witnessed directly by human eyes. Across enormous stretches of the seabed, the terrain itself remains so little explored that some of the largest features on Earth have never been seen directly by human eyes. Mountains, canyons, and landscapes no human has seen. Beyond the limits of direct observation lies a world whose geography remains surprisingly unfamiliar. Hidden beneath miles of water are vast landscapes larger than entire countries, mountain chains stretching across oceans, and valleys descending into darkness beyond the reach of sunlight. Unlike remote deserts or polar regions, these places are not difficult to see because they are far away. They remain unseen because an immense barrier of water separates them from direct human observation. Even after centuries of exploration and technological advancement, much of this terrain exists only as fragments of data collected by instruments moving far above it. The result is a strange reality in which some of the largest geographical features on Earth remain less familiar than many locations on the Moon or Mars. Many people assume the surface of Earth has already been mapped in its entirety. Modern navigation systems can pinpoint locations within meters. Satellites continuously photograph continents from orbit, and digital maps allow almost any region on land to be viewed instantly. This creates the impression that the age of geographical discovery has largely ended. Yet that assumption changes dramatically beneath the ocean's surface. Oceans cover more than 70% of the planet, and for much of human history the seafloor remained almost completely invisible. While coastlines could be charted and islands documented, the terrain hidden below remained largely unknown. For generations, maps of the deep ocean contained vast blank spaces where certainty simply did not exist. For centuries, knowledge of the seafloor depended on remarkably simple methods. Sailors attempting to measure depth relied on weighted lines lowered over the side of ships. The process was slow, labour-intensive, and capable of providing information only from a single point at a time. A vessel might travel hundreds of miles while gathering only a handful of measurements. The immense scale of the oceans made comprehensive mapping effectively impossible. Early charts could identify shallow hazards near coastlines, but they revealed almost nothing about the deeper regions beyond. Beneath shipping routes and trade networks lay landscapes whose shapes, elevations, and dimensions remained completely unknown. Everything changed when sound became a tool for measuring distance beneath the waves. During the 20th century, advances in sonar technology allowed researchers to transmit sound pulses downward and calculate depth based on the time required for echoes to return. Instead of collecting isolated measurements, scientists could begin constructing continuous profiles of the seabed. What emerged from these surveys was unexpected. Rather than a relatively featureless plain, the ocean floor proved to be astonishingly complex. Mountains, valleys, cliffs, plateaus, and enormous geological formations appeared where none had been anticipated. The hidden landscape beneath the oceans was not merely comparable to the geography of continents. In many cases, it rivaled or exceeded it. Stretching across multiple ocean basins is a mountain system, unlike any found on land. Known as the mid-ocean ridge, this immense geological feature extends through the Atlantic, Indian, Arctic, and Pacific Oceans, forming a nearly continuous chain across the planet. Its existence was not fully appreciated until the development of modern oceanographic surveying techniques revealed its true scale. Unlike mountain ranges visible from the surface, this system remained concealed beneath thousands of meters of water. Yet despite its invisibility, it represents one of Earth's most significant geological structures, marking regions where tectonic plates move apart and new oceanic crust forms. Running for roughly 40,000 miles, the mid-ocean ridge forms one of Earth's defining geological features. It is longer than any mountain range found on land and wraps around the globe like a seam running across the planet's surface. In certain locations, portions of the ridge rise high enough to emerge above sea level, creating islands such as Iceland. Most of the system, however, remains hidden beneath the ocean. The scale of the ridge is difficult to visualize because no single image can capture it in its entirety. It extends across multiple oceans, crossing regions that remain inaccessible to direct human observation. Despite its immense size, countless people remain unaware that the longest mountain chain on Earth lies underwater. While underwater mountains revealed unexpected heights, other discoveries exposed depths that were equally astonishing. Ocean trenches represent some of the deepest features on the planet, descending far below surrounding seafloor regions. These immense depressions form where tectonic plates converge and one plate is forced beneath another. Early depth measurements hinted at their existence, but only detailed surveys revealed their true scale. Certain trenches descend deeper than Mount Everest is tall, creating environments subjected to pressures so extreme that human access remains extraordinarily difficult. These locations challenge conventional perceptions of geography because their dimensions rival the most dramatic landscapes found on land, while remaining almost entirely hidden from view. Carved into continental margins and descending toward the deep ocean are enormous submarine canyons. Some rival or exceed famous surface canyons in size, yet they remain largely unknown outside scientific communities. These formations can extend for hundreds of miles, channeling sediment from continental shelves toward deeper regions of the ocean. Monterey Canyon off the coast of California, for example, reaches depths comparable to some of the largest terrestrial canyons. The existence of these structures demonstrates that familiar geological processes continue beneath the sea, in ways that are often difficult to observe directly. Rivers, landslides, erosion, and tectonic activity all contribute to shaping landscapes hidden beneath the waves. Thousands of volcanoes rise from the seafloor without ever breaking the ocean surface. These underwater mountains, known as seamounts, represent one of the most abundant geological features on the planet. Some rise thousands of meters above the surrounding seabed, creating isolated environments that influence ocean currents and biological activity. Despite their significance, many remain undiscovered. Advances in satellite measurements and sonar mapping have revealed far more seamounts than previously recognized, yet estimates suggest that thousands still await detailed documentation. The sheer number of these submerged mountains illustrates how incomplete humanity's understanding of the ocean floor remains. Certain discoveries have been so large that they fundamentally altered scientific understanding of Earth's geology. Before comprehensive seafloor mapping, many aspects of plate tectonics remained poorly understood. The revelation of mid-ocean ridges, deep trenches, and fracture zones provided critical evidence supporting theories about the movement of Earth's crust. Features hidden beneath the oceans helped explain the formation of continents, the occurrence of earthquakes, and the distribution of volcanoes across the globe. In an unexpected way, the unseen geography of the deep ocean became essential to understanding the visible geography of the world above it. Despite decades of technological progress, large portions of the seabed remain only partially surveyed. International efforts to improve ocean mapping have accelerated in recent years, yet complete coverage remains a formidable challenge. High-resolution surveys require specialized vessels, sophisticated equipment, and substantial resources. The oceans are vast, and even modern technology cannot examine every region quickly. While broad maps exist for much of the seafloor, detailed observations remain limited across significant areas. Researchers continue discovering previously unrecognized features, reminding us that major geographical discoveries are not confined to the distant past. Mapping the ocean presents challenges fundamentally different from mapping land. Satellites can photograph continents directly, but water absorbs and scatters light, preventing similar observation of the seafloor. Scientists therefore rely heavily on sonar systems carried by ships, autonomous vehicles, and other instruments. Each survey covers only a relatively narrow area compared to the immense scale of the oceans. Weather conditions, remote locations, operational costs, and technical limitations further complicate efforts. As a result, constructing accurate maps of underwater terrain often requires years of sustained work across regions that may never be visited by humans directly. Each newly surveyed region has the potential to reveal features absent from existing charts. Hidden ridges, previously unknown seamounts, and unusual geological formations continue to emerge from modern datasets. In some cases, discoveries challenge earlier interpretations based on lower resolution information. In others, entirely new questions arise regarding how particular landscapes formed. The process resembles exploration in its purest form because researchers cannot always predict what will appear when previously unmapped territory is finally examined. Even now, in an era defined by advanced technology, genuine geographical surprises remain possible. The continuing effort to understand Earth's hidden geography has produced consequences far beyond cartography alone. Knowledge gained from studying remote ocean environments has influenced geology, climate science, hazard assessment, biology, and even planetary exploration. The realization that immense dynamic landscapes could remain concealed beneath our own oceans encouraged scientists to think differently about unexplored environments elsewhere. If Earth's largest hidden terrains could evade understanding for so long despite existing on our own planet, then distant worlds might contain equally remarkable discoveries waiting beneath their surfaces. The lessons learned from mapping the deep ocean ultimately extended far beyond the boundaries of Earth itself. Lessons learned from these remote environments would eventually influence one of humanity's most ambitious scientific questions: whether life could exist in oceans far beyond our own world. The hunt for life beyond Earth begins underwater. At the edges of everything previously mapped, a new scientific question began to form that no longer belonged entirely to Earth. It did not arise from a single discovery or a sudden breakthrough, but from a gradual accumulation of evidence gathered in places where sunlight never reached, and expectations about life began to break down. As researchers studied environments shaped by pressure, darkness, and chemical energy, a subtle shift occurred in how life itself was defined in scientific terms. The ocean, once considered a boundary between known and unknown biology, started to resemble something larger in significance, a reference point for possibilities that extended far beyond planetary limits. In this growing uncertainty, the deep sea began to serve an unexpected role, not as an endpoint of exploration, but as the starting point for imagining life elsewhere. For much of modern astronomy, the search for life beyond Earth was guided by a narrow set of environmental expectations. Scientists focused primarily on planets that might resemble Earth's surface conditions, assuming that life required sunlight, stable atmospheres, and moderate temperatures. This approach was shaped by observation, since every known form of life had been found within environments influenced directly or indirectly by solar energy. Even when speculation turned toward distant planets, the underlying assumption remained consistent. Life would likely follow patterns similar to those seen on Earth. This framework shaped early missions, observational priorities, and theoretical models, creating a search strategy that was logical but limited by what had already been observed. That framework began to shift dramatically following observations made in the deep ocean during the late 20th century. Prior to this shift, the seafloor was largely considered a biological desert, with most ecosystems thought to depend on organic material falling from the surface. The discovery of hydrothermal vent communities in 1977 fundamentally disrupted that assumption. These ecosystems were found thriving in complete darkness, sustained not by sunlight, but by energy derived from chemical reactions occurring in the Earth's crust. Dense biological communities existed around these vents, supported by microorganisms capable of converting inorganic compounds into usable energy. The significance of this discovery extended far beyond marine biology, because it revealed that life could exist in environments previously thought incapable of supporting complex ecosystems. Energy derived from chemical reactions rather than sunlight redefined what conditions could potentially support living systems. This process, known as chemosynthesis, demonstrated that biological productivity did not require solar input as its primary driver. Instead, chemical gradients produced by geological activity could serve as a stable energy source. Around hydrothermal vents, compounds such as hydrogen sulfide provided the foundation for microbial ecosystems that, in turn, supported larger organisms. The existence of these systems suggested that life might arise or persist in environments shaped more by internal planetary processes than by surface conditions. As this understanding developed, it challenged long-standing assumptions about the limits of habitability, opening new possibilities for where life might exist beyond Earth. As these ideas developed, scientists began recognizing that Earth's deepest environments offered more than geological insight. They became natural laboratories for understanding how life might function in extreme and isolated conditions. The deep ocean, particularly regions far removed from sunlight and surface influence, presented conditions that could not be easily replicated in terrestrial environments. Pressure, temperature, chemical composition, and energy availability combined in ways that produced ecosystems fundamentally different from those on land. These environments did not merely expand biological knowledge, they provided a framework for reconsidering how life might operate under entirely different planetary conditions. Among the most significant targets in this emerging perspective was a distant moon, orbiting Jupiter known as Europa. Observations of Europa revealed a surface covered in ice, marked by fractures and patterns suggesting movement beneath the frozen exterior. Measurements from spacecraft and analysis of magnetic field interactions provided strong evidence that a global ocean likely exists beneath the ice shell. This hidden ocean, shielded from direct sunlight, immediately drew comparisons to Earth's deep-sea environments. If liquid water exists beneath Europa's surface, and if energy sources such as hydrothermal activity are present on its seafloor, then conditions could exist that resemble those found around Earth's hydrothermal vents. This possibility shifted Europa from a distant astronomical object into a potential environment of profound scientific interest. Further from Jupiter, another icy world began drawing attention due to active plumes detected above its surface. Saturn's moon Enceladus exhibited geyser-like emissions of water vapor and ice particles erupting from fractures near its south pole. These plumes, observed by spacecraft during flybys, offered a rare opportunity to sample material originating from beneath the surface without the need for drilling or landing. Analysis of the plume material revealed the presence of water, organic compounds, and chemical signatures associated with hydrothermal processes. The discovery suggested that Enceladus may also contain a subsurface ocean interacting with a rocky interior, creating conditions that could support chemical energy cycles similar to those observed in Earth's deep ocean environments. Beyond these two primary examples, additional celestial bodies suggested the possible existence of hidden oceans elsewhere in the solar system. Saturn's moon Titan, for instance, presents a radically different environment with lakes and seas composed of liquid hydrocarbons on its surface. While chemically distinct from water-based oceans, Titan demonstrates that liquid environments can exist under conditions vastly different from those on Earth. Other moons and planetary bodies continue to be evaluated for signs of subsurface liquid layers, expanding the range of potential habitats under consideration. Each of these worlds contributes to a growing realization that oceans may be more common in the solar system than previously assumed, even if they exist in forms that are not immediately recognizable. Translating exploration techniques from deep ocean environments to space required entirely new engineering approaches. Equipment designed for extreme underwater conditions, such as autonomous vehicles and remotely operated systems, provided valuable conceptual foundations for spacecraft intended to explore distant oceans. The challenges share striking similarities, including limited communication, extreme environments, and the need for high levels of reliability in systems operating far from direct human control. As a result, technologies developed for studying Earth's deep sea have influenced the design of instruments intended for future planetary missions. In this way, the ocean became not only a subject of scientific study, but also a testing ground for the tools of interplanetary exploration. Detecting life in such environments depends not on direct observation, but on identifying subtle chemical signatures. Scientists searching for extraterrestrial life focus on biosignatures, which may include chemical imbalances, organic molecules, or patterns that suggest biological activity. These indicators are difficult to interpret because non-biological processes can sometimes produce similar results. In Earth's deep ocean, researchers encounter this challenge directly, as geological and chemical processes can mimic signs of biological activity. Studying these environments helps refine the criteria used to evaluate potential life elsewhere, improving the ability to distinguish between biological and non-biological sources of observed signals. Interpreting these signals is complicated by natural processes that can imitate biological activity. Hydrothermal reactions, mineral interactions, and chemical disequilibria can all produce patterns that resemble those associated with living systems. This overlap requires careful analysis and often prevents immediate conclusions. Scientists must consider multiple explanations simultaneously, weighing probabilities rather than relying on definitive markers. In planetary science, where data from distant worlds is limited, this challenge becomes even more pronounced. As a result, caution remains central to interpretations of potential biosignatures, ensuring that claims of life or habitability are supported by robust and repeatable evidence. Over time, collaboration between different scientific disciplines became essential for progress in this field. Oceanographers, geologists, chemists, biologists, and planetary scientists began working together to address questions that no single discipline could fully resolve. Deep-sea exploration provided biological and geological insights, while astronomy and planetary science extended these ideas to distant environments. This interdisciplinary approach allowed for more comprehensive models of habitability, integrating observations from Earth with data collected from spacecraft. The boundaries between fields gradually became less distinct, as researchers recognized that understanding life in the universe requires knowledge drawn from multiple sources of evidence. What began as a study of Earth's most inaccessible environments gradually evolved into a framework for exploring entirely different worlds. The deep ocean, once considered remote and self-contained, became central to one of science's most expansive questions. Each discovery made beneath Earth's surface contributed indirectly to shaping how scientists approach the possibility of life beyond the planet. In this way, the ocean did not simply reveal what exists within its depths, it reshaped how humanity imagines what might exist elsewhere. The search for life beyond Earth, once directed outward into space alone, now carries with it the lessons learned from the darkest regions of our own world. Within the deepest regions of a distant ocean on Earth, conditions emerge that may closely resemble environments where entirely different forms of life could one day be found. What was found? Inside the deepest trench on Earth, direct exploration of the deepest point in Earth's oceans has continued to produce results that challenge earlier assumptions in ways few early researchers anticipated. For much of modern history, the deepest ocean trench was imagined as a place largely removed from biological and environmental complexity, a zone defined more by absence than presence, where pressure and darkness would erase nearly every possibility of life or human influence. That expectation was not unreasonable at the time, given how little direct evidence existed from depths approaching 11 kilometers beneath the surface. Yet as technology advanced and exploration slowly became possible, the trench began to reveal conditions that did not fully match those early expectations, forcing scientists to reconsider what inaccessible truly meant in a physical sense. The first attempts to physically reach these depths marked one of the most extreme technological achievements in ocean exploration. In 1960, Jacques Piccard and Don Walsh descended into the Challenger Deep aboard the bathyscaphe Trieste, a vessel designed to withstand pressures that exceed 1,000 times those at sea level. Their descent remains one of the earliest human encounters with the deepest known point in the oceans, a location that had previously been understood only through indirect measurements. At nearly 11,000 meters below the surface, they reported limited visibility through thickened glass and an environment dominated by silence and darkness, where even basic assumptions about movement and sound behave differently than in shallower waters. Although their time at the bottom was brief, the descent confirmed that human-made vessels could physically reach a region once considered entirely beyond contact. At nearly 11,000 meters below the surface, the physical conditions reach limits that reshape almost every known form of matter. The pressure at these depths is so extreme that even the structure of biological tissue and engineered materials behaves differently than in shallow environments. Water itself becomes a medium that exerts forces far beyond human experience on land, compressing equipment, distorting acoustic signals, and limiting nearly every form of direct interaction. Temperatures remain near freezing, and sunlight is entirely absent, creating an environment where energy sources are scarce and conditions appear hostile to most known life forms. Yet despite these extremes, the trench is not an empty void, and the assumption of lifelessness has gradually been replaced by a more complex understanding of what can survive under such pressure. Despite these conditions, scientific expeditions have confirmed the presence of living organisms in the Hadal zone. Among the most notable are small crustaceans and microbial communities capable of surviving under immense pressure, often found within sediments or near the seafloor. These organisms do not resemble familiar surface life in scale or behaviour, yet they demonstrate that biological processes can continue, even in environments once thought entirely uninhabitable. Their presence suggests that life does not simply tolerate extreme conditions, but can adapt to them in ways that remain only partially understood. Each discovery at these depths has expanded the known boundaries of biology, showing that even the most remote regions of the planet contain active, functioning ecosystems. Survival at such extreme depths requires biological adaptations that operate far beyond surface-level expectations. Cellular structures must remain stable under crushing pressure, and biochemical processes must function without the structural collapse that would occur in most known organisms. Some species appear to rely on modified proteins and cellular membranes that maintain flexibility in conditions that would otherwise be destructive. Others utilize metabolic strategies that are extremely efficient in low-energy environments, where food sources are scarce and sporadic. These adaptations do not merely represent incremental changes, but fundamental adjustments to the constraints of one of the most extreme environments on Earth. In recent decades, repeated surveys have revealed that these environments are more biologically active than once believed. Rather than isolated pockets of survival, the Hadal zone contains interconnected systems of life that persist across vast stretches of trench terrain. Sediment samples and imaging surveys have shown that organisms are not limited to isolated points, but can be found distributed across multiple regions of the trench floor. This distribution suggests that biological activity at these depths may be more stable and widespread than early models predicted, even if it remains far less dense than in shallower ocean zones. Each new expedition adds additional complexity to a picture that was once assumed to be simple or empty. Among the most surprising findings from deep trench expeditions has been the presence of human-made materials. Plastic debris, once thought unlikely to reach such extreme depths, has been discovered in sediment samples from the Mariana Trench and other deep ocean locations. These materials are not simply floating fragments, but are embedded within the geological record of the seafloor, indicating that human influence extends far deeper into the planet than previously assumed. The presence of manufactured materials at these depths challenges earlier assumptions that isolation would protect the deepest parts of the ocean from surface activity. Instead, it reveals a continuous exchange between human systems and environments once considered completely separate from them. Chemical analyses of deep-sea samples have identified traces consistent with long-range human industrial activity. Persistent organic pollutants and microplastic particles have been detected in sediments far removed from direct sources of contamination. These substances are transported through complex oceanic processes, eventually accumulating even in the most remote regions of the planet. The discovery of these chemical traces demonstrates that human activity is not confined to visible or immediate environments, but has become a planetary-scale phenomenon. Even locations that appear physically unreachable are connected through systems of circulation that distribute materials across vast distances and depths. These findings stand in contrast to earlier assumptions that such depths would remain completely isolated from surface influence. For a long time, the deepest trench was imagined as a closed environment, protected by distance and pressure from the effects of human civilization. However, modern observations have shown that no part of the ocean exists entirely outside global environmental systems. Currents, sediment flows, and biological transport mechanisms all contribute to a slow but continuous movement of materials into regions once thought untouched. The trench, rather than being separate from the surface world, is part of a larger interconnected system that spans the entire planet. Exploration of the deepest trench relies on highly specialized vehicles capable of surviving conditions that destroy conventional equipment. Manned submersibles and remotely operated vehicles must be engineered with extreme precision to withstand pressure that can crush standard materials instantly. Communication with these vehicles becomes increasingly difficult as depth increases, with signals distorted by water density and distance. Each descent represents a significant logistical and technological challenge, requiring extensive preparation and limited operational windows. As a result, only a small number of missions have successfully reached the deepest known points of the ocean, making each exploration highly valuable in terms of scientific return. Each new descent has reinforced the realization that even the most remote parts of the planet are not entirely untouched. The expectation of absolute isolation has gradually been replaced by an understanding of interconnectedness, where biological, chemical, and even human influences extend far deeper than once imagined. The trench is no longer viewed solely as a geological curiosity, but as a dynamic environment influenced by both natural processes and global-scale human activity. This shift in understanding has redefined how scientists interpret extreme environments, not as separate or sealed systems, but as part of a continuum that connects the surface and deep ocean in unexpected ways. Yet despite decades of investigation, repeated returns to these depths remain relatively rare compared to other regions of the ocean. The technical difficulty, cost and risk associated with deep trench exploration limit the frequency of missions, and many areas remain only sparsely observed. As a result, each expedition still has the potential to reveal new information, reinforcing how little direct observation exists at the planet's deepest points. The scarcity of data contributes to an ongoing sense of uncertainty, where even well-established assumptions remain open to revision as new evidence emerges from future descents. The reasons for this limited return become clearer when considering how few technologies can endure repeated exposure to conditions that push the limits of engineering itself. Why so few people go back? Following direct observations from the deepest known point in the ocean, a broader question emerges about how often such environments are actually revisited. The expectation, especially outside scientific circles, is that once a location of such significance has been reached, it becomes a regular destination for further study, gradually refined through repeated observation and increasingly advanced equipment. Yet the reality of deep ocean exploration does not follow that pattern. Instead, it is defined by long intervals between visits, limited opportunities for deployment, and a constant balancing act between ambition and practicality. What has been discovered in the abyssal depths is therefore shaped not only by scientific curiosity, but by the constraints that determine when, how, and whether such curiosity can be acted upon. Public perception often assumes that the deepest parts of the ocean are regularly surveyed by scientific missions. This assumption is understandable given the visibility of exploration in other domains, where satellites continuously orbit Earth, telescopes observe distant galaxies, and spacecraft routinely visit planetary bodies. In contrast, the ocean floor does not produce visible reminders of ongoing study, and so it is often imagined as being subject to continuous exploration. However, deep-sea missions represent a very small fraction of global scientific activity. Even major trenches and abyssal zones may go years without a dedicated expedition, and in some cases decades pass between detailed revisits. The silence between these missions contributes to the impression of continuity, when in fact the record is fragmented and intermittent. In reality, expeditions to extreme ocean depths occur far less frequently than most people assume. Only a limited number of specialized vessels in the world are capable of reaching Adal depths, and their availability is often shared among multiple research programs, governments, and institutions. Each mission requires extensive preparation, careful planning, and precise coordination across scientific, engineering, and logistical teams. Weather conditions must align, equipment must be tested repeatedly, and support systems must be in place to ensure safe deployment and recovery. Even when all conditions are met, operational windows are narrow and delays are common. As a result, opportunities to access the deepest regions of the ocean remain rare events rather than routine operations. One of the most immediate limiting factors in deep-sea exploration is the extreme cost associated with each mission. Operating a deep-diving submersible or remotely operated vehicle requires not only the construction and maintenance of highly specialized equipment, but also the deployment of research vessels capable of supporting long-duration offshore operations. These ships must carry crews, laboratories, fuel, spare parts, and advanced communication systems, often for weeks or months at a time. The financial cost of such expeditions can reach levels that restrict their frequency, even for well-funded institutions, unlike satellite-based observation, which can provide continuous data once deployed. Deep-sea exploration demands repeated investment for each individual mission. Beyond financial constraints, the engineering requirements for surviving deep ocean pressure impose significant limitations on equipment design. At depths approaching those of the deepest trenches, pressure reaches levels that can exceed 1,000 times that at the surface, placing extraordinary stress on materials, seals, electronics, and structural components. Every part of a deep diving system must be designed with redundancy, durability, and failure resistance in mind. Even minor imperfections in construction can lead to catastrophic failure under pressure. This means that equipment must be carefully inspected and often rebuilt or extensively refurbished between missions, further limiting how frequently it can be deployed. Even when technology succeeds, human involvement introduces additional layers of risk that must be carefully managed. Manned submersibles offer direct observational advantages, but they also expose crews to environments where survival depends entirely on the integrity of the vessel. While modern engineering has made such descents possible, the inherent risk remains significant, particularly in regions where rescue or recovery is impossible within meaningful timeframes. For this reason, many modern deep ocean missions rely on unmanned systems, reducing human risk but introducing new technical constraints related to communication latency, control precision, and operational autonomy. The logistics of deploying deep-sea missions are often more complex than the exploration itself. A single expedition requires coordination between shore facilities, research institutions, vessel operators, engineers, scientists, and sometimes multiple national agencies. Equipment must be transported, assembled, tested, and maintained under conditions that can change rapidly due to weather or mechanical issues. Once at sea, operations are further constrained by ocean conditions, including wave height, currents, and seasonal variability. Even minor disruptions can delay deployment or force early termination of a mission, reducing the already limited number of successful dives. In addition to technical challenges, deep ocean research is influenced by international coordination and jurisdictional boundaries. While much of the deep ocean lies beyond national territorial waters, research programs are still shaped by funding sources, regulatory frameworks, and collaborative agreements between institutions and countries. These structures determine access to vessels, equipment, and data, often requiring long-term planning and negotiation before a single expedition can take place. As a result, scientific exploration in the deep ocean is not only a technical endeavour, but also an organisational one, shaped by systems that extend far beyond the sea itself. Scientific institutions must also allocate limited funding across a wide range of competing research priorities. Oceanography competes with fields such as climate science, biology, geology, and space exploration for financial resources and institutional support. Even within ocean science, priorities must be divided among coastal studies, fisheries, climate monitoring, and deep-sea exploration. This distribution of resources means that only a fraction of available funding can be directed toward extreme depth missions. As a result, even when interest is high, the practical ability to sustain continuous exploration remains constrained. Modern remote sensing technologies have improved access to data, but they cannot fully replace physical exploration. Satellite observations and wide-area sonar mapping can reveal large-scale structures and general seafloor features, but they lack the resolution and specificity required to understand fine-scale processes or biological communities. Direct sampling remains essential for confirming hypotheses analysing organisms and validating environmental models. This creates a persistent gap between what can be inferred remotely and what can only be confirmed through direct presence, reinforcing the need for physical expeditions despite their rarity. Repeated visits to the same deep-sea locations are essential for accurate long-term understanding, yet remain uncommon. Environmental conditions in the deep ocean can change over time due to geological activity, sediment movement, and biological shifts. Without repeated observation, scientists are often limited to isolated snapshots, rather than continuous records. However, the cost and difficulty of organising repeat missions mean that many regions are studied only once or a few times, leaving significant gaps in long-term datasets. This limitation affects not only oceanography, but also broader fields that depend on stable environmental baselines. When compared to space exploration programs, ocean exploration receives a significantly smaller share of sustained investment. Missions to other planets often benefit from long-term strategic funding and public visibility, while deep-sea exploration tends to operate within shorter funding cycles and narrower institutional frameworks. Despite the fact that the ocean lies far closer and is physically more accessible than space, its exploration infrastructure is less developed and less consistently supported. This imbalance reflects historical priorities as well as differences in public perception, where space exploration often captures more attention than underwater research. As a result, access to the deepest parts of the ocean is determined less by curiosity than by the practical limits of global scientific infrastructure. The willingness to explore exists across many disciplines, but the ability to act on that willingness depends on resources, technology, coordination, and time. In this sense, the rarity of deep ocean expeditions is not a reflection of diminished scientific interest, but of the complexity involved in sustaining such efforts over repeated cycles. The ocean remains open to exploration, but only intermittently accessible under conditions that must align with precision. These constraints suggest that much of what remains unknown beneath the ocean is not hidden because it cannot be reached, but because reaching it repeatedly is far more difficult than most assumptions about exploration would suggest. The vast unknown waiting below. As the limitations of deep ocean exploration become clearer, they also reveal a broader pattern about how little of the planet has been fully resolved at a fine scale. The sense of completion that often accompanies global mapping is, in many ways, an artifact of visualization rather than a reflection of uniform knowledge. While digital representations of Earth suggest continuity and precision, they are built from layers of data that vary dramatically in resolution, depending on location, depth, and accessibility. Beneath the surface of that apparent clarity lies a more fragmented reality, where entire regions of the ocean floor are known only through sparse measurements, separated by vast distances. The result is not a fully assembled picture of the seafloor, but a mosaic composed of differing levels of certainty. Despite the appearance of comprehensive global mapping, large portions of Earth's ocean remain far less resolved than most terrestrial environments. On land, even remote regions can often be surveyed directly, photographed and revisited with relative ease. In contrast, the deep ocean resists consistent observation, and the tools used to map it do so indirectly through sonar, satellite-derived gravity data, and limited direct sampling. These methods provide valuable insight at large scales, but they do not produce the same level of detail achievable on land. As a result, the ocean floor often appears smooth or generalized in global models, even in regions where the actual terrain is likely far more complex. Modern seafloor maps often create an impression of continuity that masks significant differences in data resolution. Certain areas, particularly those near coastlines or along major shipping routes, have been mapped with relatively high precision due to repeated surveys and strategic importance. Other regions, especially in the deep ocean basins, remain represented by data collected during infrequent passes of survey vessels. When viewed at a global scale, these differences can be difficult to distinguish, giving the impression of uniform knowledge where none exists. This disparity between perception and measurement is one of the defining characteristics of modern ocean science. Even today, vast regions of the deep ocean are represented by relatively low-resolution measurements. In some cases, features smaller than several kilometers may not appear in global datasets at all, effectively rendering them invisible within standard representations of the seafloor. This does not mean these features are absent. only that current mapping techniques are not always capable of capturing them in detail. The deeper and more remote the region, the greater the likelihood that its true structure remains only partially defined. As technology improves, previously unseen features continue to emerge, gradually refining but never fully completing the global picture. Within these gaps, scientists continue to identify geological structures that suggest far more complexity than current maps fully capture. Seamount chains, fracture zones, and previously unrecognized ridges have been revealed through higher resolution surveys, often in areas once thought to be relatively uniform. Each new dataset adds depth to the understanding of oceanic geology, but also highlights how much remains uncertain. The ocean floor is not static in its interpretation. It evolves with each improvement in measurement, revealing that what was once considered known may represent only a simplified version of a more intricate underlying structure. Some of the most remote ocean regions may still contain major geological features that have not yet been directly observed. While broad-scale surveys can suggest the presence of large formations, confirmation often requires targeted expeditions that are difficult to conduct at the necessary scale. This means that certain structures may remain inferred rather than directly documented for extended periods. In such cases, scientific understanding relies on indirect evidence, which must later be validated through physical exploration. The delay between inference and confirmation is a persistent feature of deep ocean science. Biological sampling across the deep ocean remains too limited to define the full extent of life in extreme environments. While researchers confirm the presence of organisms in a wide range of deep-sea habitats, these findings are based on relatively small numbers of expeditions compared to the vast size of the oceans. Many regions have never been sampled directly, and others have been visited only briefly. As a result, the distribution of life in the deepest parts of the ocean is still only partially understood. Each new expedition has the potential to extend known biological ranges, but also to reveal unexpected absences that raise further questions. Chemical processes occurring in isolated parts of the ocean are still only partially understood due to sampling constraints. The ocean is a dynamic chemical system in which elements are constantly exchanged between water, sediment, and biological activity. However, the sheer scale of the environment means that only a fraction of these processes can be directly measured at any given time. Localized studies provide detailed insight into specific regions, but they cannot fully capture the variability that exists across the entire ocean system. This limitation means that global chemical models often rely on extrapolation from incomplete datasets. The same physical barriers that restrict exploration also limit the frequency and scope of data collection. Depth, pressure, remoteness, and environmental conditions all contribute to the difficulty of conducting sustained surveys in the deep ocean. Equipment must be transported to remote locations, deployed under carefully controlled conditions, and recovered without failure in environments where repair is impossible. These constraints make continuous observation impractical in most regions, reinforcing the episodic nature of deep ocean science. Each mission becomes a temporary window into a system that otherwise remains largely unobserved. Because ocean conditions change continuously, even detailed surveys represent only temporary snapshots of a dynamic system. Currents shift, sediments move, biological activity fluctuates, and geological processes continue beneath the surface. This means that no single dataset can fully represent the state of the ocean over time. Instead, scientists must rely on repeated observations that gradually build a more complete understanding. However, the infrequency of such observations means that long-term continuity is difficult to achieve, and many changes may occur between measurements without immediate detection. This means that what is considered known in ocean science often depends on the resolution of available measurements. As technology improves, previously hidden details emerge, and earlier interpretations must sometimes be revised. Knowledge of the ocean floor is therefore not fixed but adaptive, shaped by the tools used to observe it. What appears smooth in one dataset may appear highly complex in another, depending on the scale and precision of measurement. In this sense, the ocean is not simply being mapped. It is being progressively revealed through layers of increasing resolution. Over time, researchers have come to accept that complete mapping of the ocean may not be achievable in a fixed or final sense. The combination of scale, depth, and logistical limitation ensures that there will always be regions with less detail than others. This does not represent a failure of science, but but rather a recognition of the inherent characteristics of the environment being studied. The ocean is too large, too deep, and too dynamic to be fully captured at once. Instead, it must be understood as an evolving data set, continually refined but never entirely complete. In this context, the ocean is understood not as a fully charted environment, but as a system that continuously exceeds the limits of observation. Each generation of technology reveals new aspects of its structure, but also exposes new gaps in understanding. The deeper the exploration goes, the more apparent it becomes that knowledge of the ocean is always partial, always provisional, and always subject to expansion. Rather than reaching a final state of comprehension, ocean science operates within an ongoing process of discovery without closure. Even with centuries of exploration behind it, the ocean continues to suggest that what lies beneath its surface is defined less by what has been discovered than by what has yet to be seen.